Hey, Physics 35 IBs. Welcome to your engineering physics unit. We're going to go through the first section today. And hang on a second. Don't hit that button. There you go. Okay, so for the first section, rigid bodies and rotational dynamics. What we're doing is we're going to take regular, good old-fashioned physics 20 and 30 kinematics, dynamics, energy in terms of kinetic energy and momentum, and change that from our regular linear frame of reference to a rotational frame of reference, something going around in a circle. So we're going to talk about things, just start off talking about kinematics. So for measuring distance around the circle, before we measured just good old meters back in physics 20, 2 pi r over t if we're dealing with circular motion. But here we're going to deal with not meters, but the angular displacement, like what the angle of the displacement is going around the circle. So the angle moved around a circle by an object where its circular motion starts is known as angular displacement. So you probably learned about this in math class, where you have an arc length here, A to B. The arc length, we're going to call that S. And here we've got our angle subtended by that arc, theta. So the angle theta, measured in radians, is defined as the arc length divided by the radius. So here's the arc length, S. Here's the radius, R. So we don't use radians. We don't use degrees for this. We use actually radians. So that radian mode in your calculator, now you can finally use it for something in Math 30. As a matter of fact, when you're doing your word problems involving rotational dynamics, your calculator has to be in radian mode if you're doing sine, cosine, tangent, stuff like that. We'll get to that. Okay, so radians and degrees, this should be a review for you guys when you took unit circle back in Math 30, but going around the circle once means you're going around the whole entire circumference, a distance of 2 pi r. Okay, so for linear motion, just regular speed, speed equals distance divided by time. And for circular motion, if we're talking about angular velocity, it is the angular displacement over time. So change in distance divided by change in time. Here it's the change in the angle theta, which is this from before, this right here. So it's the change in the central angle divided by time. So we're talking about displacement here in terms of radians. The symbol for that is this Greek letter here, omega. So because in one oscillation, 2 pi radians are completed in one period, so this is, again, distance divided by time in terms of radians, so 2 pi over t. And if we put that together, because frequency is 1 over period, we get this formula that's on your data sheet. Angular speed equals 2 pi times the frequency of rotation. Okay, so linking angular and linear speeds, just comparing the two. So here we've got, before we had linear speed going around and around and around in so many meters per second. Here, instead of, again, meters, we talk about radians. So the total angle in one rotation is 2 pi radians. So if you remember from Math 30, the circumference of a circle, 2 pi r, the total angle in one rotation is 2 pi radians. So distance divided by time, here's the linear speed. This is familiar looking circumference and period. Well, the angular speed in radians per second, again, distance around the circle in terms of that angle is 2 pi. So distance divided by time, angular displacement divided by period. So notice when we can kind of combine these two formulas together, the angular speed is 2 pi over t, so right there, 2 pi over t. So we can stick in angular speed right here, and we get this. Linear speed is angular speed times the radius. All right, so what if you've got something that's accelerating? Angular acceleration. So we learned back in physics 20, when an object experiences an unbalanced force, it will cause it to accelerate. We talk about forces in a circular context or an angular context as a torque. If an object experiences a torque, which is a force causing rotation, it's going to have an angular acceleration. Angular acceleration, the symbol for that is alpha. Angular acceleration is defined as the rate of change of angular velocity with time. So very familiar definition of an acceleration, change in velocity over change in time. Here we've got change in angular velocity over change in time. Instead of the units for linear velocity being meters per second squared, here we've got the units being radians per second squared. Okay, so here at the bottom, I've sort of made a comparison between physics 20, good old physics 20 formulas from kinematics, and this is how they appear on the data sheet for IB. So VI is actually U, and VF is V. Displacement is represented as S. Acceleration is still A. So just different symbols, but same looking equations. You'd be able to recognize all of these as, you know, VF equals VI plus AT, and these ones are familiar looking. But in the context of angular kinematics, here's your angular velocities and angular accelerations, angular displacement for theta. So basically, when you guys are, if you choose to, look over your word problems for your data sheet, they're going to be very, very straightforward. It's going to be very much like the kinematics word problems you got for linear situations, but instead you're going to be dealing with angular final velocity, angular initial velocity, angular acceleration, and angular displacement. But it's the same equations, so it's pretty straightforward. Okay, moment of inertia. Inertia, if you recall, is a property of an object that resists acceleration. So when something has more mass, it's got more inertia. So for translational motion, that's what we're used to. So like curling rock versus hockey puck. Curling rock has more mass, therefore it's got more inertia. So for translational motion, the inertia of an object only depends on its mass. However, if you've got an object that is rotating around and around and around and around, the resistance to change of rotational motion not only depends on its mass, but it also depends on the distribution of mass around the axis of rotation. So here, I've got a link for a video here, and I'm going to put all these links up as well. You'll see them when you open up the Google Classroom assignment. But you've got two cones here, and they're of the same mass. Mass A equals mass B. But one would imagine, so here's a cone, and you put like a stick through the skinny end, so to speak, and then you rotate that around. Most of the mass is far away from the center of rotation versus this. If you put that center of rotation through the sort of the fat end with the more mass, one would be much more easier to spin around and want to have more inertia than the other. So again, moment of inertia depends on the distribution of mass around the axis of rotation. Okay, so the simplest object to consider if you're talking about moment of inertia is a point mass. So what if you've got mass m going around and around and around and around in a circle, like say a ball end of string or something like that? The moment of inertia of a point mass m rotating at a distance r from the axis of rotation is moment of inertia symbolized by I, m times r squared. Okay, so but if you've got an actual something just besides a point, but you've got something like this, for example, well, the moment of inertia of any real mass can be determined by the sum of the individual moments of inertia of its particles. So if you've got an object made up of, n particles, it's the sum of the individual moments of inertia of all of the particles put together. Did I say that? Yeah. When you guys are looking through on your word problems, you will see that for a particular shape, each particular shape that you might be asked to do some calculations with has its own formula for calculating its own moment of inertia. So for example, a cone has its own formula. A cylinder has its own formula. I don't know, a sphere has its own formula for determining its moment of inertia. And it's not like you need to memorize any of those. You will just be given those. So on your worksheet, you'll see that I've given you a table with different moments of inertia for different shapes. And in a word problem, you'd just be given the formula. So it's not exactly rocket science. You can figure out the moment of inertia. The two variables are mass and just an average sort of radius, so to speak. Okay. A couple of examples of use of moment of inertia sort of as an application. There's a couple links there I'm going to get you guys to watch. Flywheel. Flywheels are designed to have a large moment of inertia. They're added to the axis of machinery to resist changes of motion and or to store rotational kinetic energy. So here's a potter's wheel, for example. So you put your clay on the top here and you get this thing going around and around and around. You can make your clay pot or whatever. Here on the bottom, we've got a flywheel. And that flywheel is very massive. And once it gets going, it's got a lot of inertia. Its moment of inertia is very high. Therefore, it's kind of hard to stop it from rotating once you get it going because it's high inertia. So it's like storing an amount of rotational kinetic energy. Okay, torque. So remember, torque is a force that causes something to rotate or twist or turn or something like that. Like if you turn a doorknob or you turn a steering wheel of your car or something like that, you're applying a torque. Or a wrench, like this. The line of action of a force is a straight line showing the direction in which the force is applied. Any force applied to an object whose line of action is not through the axis of rotation will tend to change rotational motion if that's possible. So let's take a look at this diagram right here. You are turning a wrench on a nut here, and the most efficient way to turn that wrench would be to apply a force at a 90-degree angle to this radius right here. So this would be the most efficient line of action. The line of action that would produce the least amount of torque, which would be 0, is if you just, took a wrench and you pushed on the wrench right towards the nut. Like that would not cause any rotation whatsoever. So this is the maximum and this is the minimum, and then there's variations in between. Like if you push at an angle kind of like that, like it's showing there, it will cause some torque, not as good as if you push it at a 90-degree angle to this line right here like this. Again, I will put any link that you see right here like this, I will put as a link in terms of the assignment in the Google Classroom. So check those out as well. Okay. In general, the turning effect of a force is known as its torque. That is the Greek letter. Ooh, I should know that. It kind of looks like a funny looking T. Hang on. I don't care. I'm not going to edit this out. You guys don't care, do you? I'm going to look up what that Greek letter is. I'm pretty sure it's tau, but I don't remember. Oh, come on. Oh, here. Yeah, tau. T-A-W. Look at that. I got it. Okay. So here's your torque represented by tau. The units for torque, Newton meter. The force in newtons are radius, so it kind of makes sense. Radius would make sense because if we, were to push really close to the nut on a wrench versus like really far away, one would assume, like, just imagine doing that, right? It would be much easier if you've got a longer wrench to apply a greater torque. So the radius definitely matters. Whoops. And that angle between the force and the radius in degrees. So it's a maximum when that angle is equal to 90 degrees. So here's another formula on your data sheet. Maximum torque occurs when the force is perpendicular to the radius. So theta equals 90 degrees, and the sine of 90 degrees is 1. So that sine expression goes away there, and you're just left with FR. So notice I said Newton meter. The unit for torque is not equivalent to a joule, even though it's Newton meter, but torque is a vector quantity, whereas energy is scalar. Couples. A couple is the name given to a pair of equal-sized forces that have different lines of action, but are parallel to each other and act in opposite directions, tending to cause rotation. So best example of a couple, you got both hands on a steering wheel, you're like at 10 and 2 or 9 and 3 or whatever, and you do this to turn the wheel. Well, one hand is exerting a force up on the wheel, like say here, and the other force is exerting a force down. So these two forces are parallel to each other, and they're both causing the wheel to turn. So that's a couple. Okay, so let's say if a single force, you've got a bat right here. A bat is standing up on end here. And what if you put a force here, or here, or there? So let's say if a single force acts on an object, which is free to move, like this bat, but not through its center of mass, it will tend to change both its rotational and translational motion. So what that means is if you imagine, you've got a bat standing up and you apply force on the top, it's going to move it to the right. Like the whole bat's going to move, but it's also going to tip it over. So what that means is it causes translation. So it causes it to move from one place to the other, and it causes it to rotate as well. Okay, so Newton's laws for angular motion. So first law, law of inertia. Second law, basically F equals ma for linear. And third law, action-reaction. Every action has an equal and opposite reaction. So we're taking those same three laws and then changing it from a linear frame of reference to a rotational frame of reference. So first law, translational and rotational equilibrium. Translational equilibrium occurs when the forces acting on an object are, oops, little typo there. I know a certain somebody is going to point that out if they were in class. There you go. Are balanced so that it remains either at rest or at a constant velocity. So same thing. When an object is experiencing balanced forces, it remains at rest or at a constant velocity. Rotational equilibrium, however, so it's going to remain rotating at a constant velocity or at rest, is when there is no resultant torque acting on an object. So same thing, but in a different circular or angular context. For the second law, for linear motion or translational motion, when an unbalanced force acts on a mass, it produces a linear acceleration. For rotational motion, when an unbalanced torque, represented by tau, acts on an object with a moment of inertia, I, again, it depends on the distribution of mass around the center of rotation, it produces an angular acceleration, alpha. And the third law, action-reaction. Action torque and reaction torque are equal and opposite. That's it. Now, angular momentum, moving into sort of physics 30 stuff. So remember, linear momentum is used to analyze the behavior of objects involved in collisions. So as long as no external forces act on a system, the total momentum of all the objects in the system before the collision and after the collision remains the same. So good old P equals mv, momentum, mass times velocity. Now we've got angular momentum. We're not dealing with mass anymore. We're dealing with moment of inertia. We're not dealing with linear velocity. We're dealing with angular velocity, not in meters per second, but in radians per second. So the formula is analogous, just different symbols. So angular momentum, represented by capital L, is the rotational equivalent to linear momentum. So P equals mv, L equals I omega. The total angular momentum of a system is constant, provided that no external forces are acting on it. So this is a really cool video. You should definitely check it out, where you've maybe seen figure skating on TV or something like that, where you've got a figure skater where their arms are out really, really far. And when they bring their arms in like this, they go faster and faster and faster and faster and faster. It's really cool looking. And then to slow themselves down, they can put their arms out again. And then they bring their arms in, they go faster and faster and faster. So assuming that the angular momentum, we're ignoring friction here, but it's assuming the angular momentum of that figure skater remains constant, if we ignore the fact that there's external forces like friction acting on the tip of the blade on the ice, because angular momentum has to stay the same, and it's just these two quantities, I'm pointing at the screen, these two quantities right here. If this is constant, if the momentum of inertia goes up, this goes down. If the momentum of inertia goes down, then the angular velocity goes up. So when the figure skater brings her arms in and brings, basically what it does, it lowers the moment of inertia, because more mass is around the R in that term is less. So if the center of mass is, most of the mass is concentrated around the center of mass, then the moment of inertia goes down, and that must mean then that the angular velocity speeds up or increases, and vice versa. By extending her arms here, you've got a larger moment of inertia, therefore smaller angular velocity. Okay, last thing, rotational kinetic energy. So rotational kinetic energy analogous to translational kinetic energy. Translational kinetic energy 1/2 mv squared. Rotational kinetic energy 1/2 times the moment of inertia times the angular speed squared. So now we can actually address rolling. In physics 20 and physics 30, we just sort of ignored rolling. We talked about cars driving and stuff like that quite a bit, but we ignored the rolling of the wheels, because rolling is actually complex in terms of analyzing it in terms of the physics involved. But when an object is rolling, it has both translational kinetic energy, in that it goes from one place to the other, and rotational kinetic energy. As it gets spinning faster and faster, its rotational kinetic energy increases. So this is basically what we dealt with for all our pictures in our physics 20 textbook. We just had, like, boxes sliding across the floor, or a frictionless surface or something like that, where it's only translational kinetic energy, so it's not spinning. So all the particles of the object move together at the same time in a linear fashion. Then when we got into the chapter 5 for the rotational circular motion unit, where we just considered an object spinning around and around and around. So basically we had the ball on the end of a string going around and around and around. We only have rotational kinetic energy. But let's say you've got a wheel that is rolling. It has both rotational kinetic energy and translational kinetic energy. So an object such as a ball or a wheel that can roll down a hill will transfer its gravitational potential energy not only to translational kinetic energy, but also rotational kinetic energy. So there's a word problem involved on your sheet where you've got conservation of energy. So it's normally for like a physics 20 kind of a thing, we'd have like an object roll or slide down a frictionless incline, so to speak, where all of its potential energy is converted to kinetic energy. So mgh at the top equals 1/2 mv squared at the bottom. However, if you have an object rolling down the hill, you're going to have both rotational and translational kinetic energy. So its potential energy at the top will be equal to the sum of its translational kinetic energy plus rotational kinetic energy at the bottom. So you have to take both into account when you have something that is rolling. Here's a little summary of the things we just finished talking about. We've got comparing just straight down the middle here, linear versus rotational mechanics. Here we've got our kinematics equations in a linear context. Here's the kinematics equations in a rotational context. Then we talked about forces, 3 laws linear, 3 laws in terms of rotation, momentum, and kinetic energy. So some big ideas that we learned about all through physics 20 and 30, but now we're taking it all and squishing it into one section for the engineering physics, but taking the context from a straight line to a system that's going around and around and around. All right, so that's it for the first section. The first section is relatively short. The second section's long. It's kind of like that circuits unit that we did where the second section seemed to take forever, and this is kind of like that too. So I'm not really sure if I'm going to break up the second video into parts because, I don't know, do I want to record an hour video for you guys? It would be, God, lame. Anyway, I don't know. So this is the first video. Anyway, try some of the questions from the worksheet. Again, your exam, I'm going to use quotes here, is very much open book for this. So we're going to go through our 4 sections in the engineering physics thing. I'm going to give you a quiz at the end. It's going to be open book. I need to generate some kind of a mark for you guys, and I want that mark to be as high as possible. So anyway, see you next time.